I think we can start. I'd like to welcome all of you again on our DFI Middle East Chapter Tea Time Technical Talks program. Today, we are very much delighted to invite a very special topic delivered by a very special professional, Dr. Rodaina Abul Hassan, who works as a lecturer and researcher at ESTP in Paris, in France, since 2018. Dr. Rodaina has obtained her undergraduate degree in geotechnical engineering from the Lebanese University in Beirut, Lebanon. She received her PhD in civil engineering, mechanics, and materials from University of Grenoble-Alpes at Grenoble in France in 2017. Her research projects include developing discrete numerical models to study the effect of internal erosion on the mechanical behavior of granular soils and to model the behavior of soils once subjected to complex loading paths. Her current research includes smart geotechniques, developing artificial intelligence models, and applying IoT in geotechnical engineering. Today's topic, Dr. Abul Hassan will give us a background and will shed the lights on the artificial intelligence applications in geotechnical engineering, what challenges and what advances are there. I hope that she will give us a lot of important thoughts for our future applications in this part of the world. So Dr. Abul Hassan, the floor is yours. Thank you.
Thank you. Hello, everyone. Well, first of all, I'd love to thank DFI for this invitation to this webinar today. It's a pleasure to present one of the topics that nowadays it's almost impossible to escape from. We are living today in a world where information and data generation is growing exponentially, and in parallel, there is an impressive development of new technologies and new concepts. So we already noticed that in the field of geotechnical engineering, there is currently an explosion of innovations linked to this development. So in this presentation, I'll talk about how artificial intelligence systems are used to predict many aspects of geotechnical engineering. So just first few words about this presentation, how I organized it. So first I will start by an overview of artificial intelligence. And then in this part, I will be defining AI and the major AI techniques used nowadays. And then I will talk about the major AI techniques, and especially I'll be describing artificial neural networks, because then the applications that I'll be showing, they are done using this method. And in the second section, I talk about AI in geotechnical engineering. What are the benefits? What are the challenges that we are facing? And then I will talk about some examples of applications related to the prediction foundations during capacity and settlement, and another application related to modeling the mechanical behavior of railway ballast using artificial intelligence. And finally, I'll conclude this presentation by talking about the future of AI in geotechnical engineering. So starting with the first section, an overview of artificial intelligence. So what is artificial intelligence? How can we define AI? In fact, AI, it is a broad branch of computer science, and its main focus is on the capacity or capability of machines to behave like humans, to learn and to think. So in other words, AI, it is a computer program that is programmed in a way to mimic how humans learn and think, or how they perform tasks that we usually rely on humans to perform. So AI techniques, in order to understand how the AI model works, in fact, the best way is to compare it to how humans learn. So for example, if we take the example of a child who's learning how to ride a bicycle, a child would first get on the bicycle and start biking. He would fall down, then get up again, fall down, get up again. So the child, in fact, he doesn't learn how to ride a bicycle by understanding the physics behind, but rather by trial and errors. So over time and with lots of trials, a child will understand what are the factors that lead to lose control of the bike. So similarly to how a child learns how to ride a bicycle, in AI models, in fact, these models, they depend on repeated simulations in order to learn what is the relationship between data inputs and data outputs. So the essence of AI is two examples. That's why we call AI models data-driven models, which means that they rely only on data to determine the structure of a phenomenon. So by giving an AI model a data which consists of inputs and the corresponding outputs, an AI model should be able to capture a functional relationship between inputs and outputs. And so this relationship can allow this model to predict a given behavior or give a decision, which is then analyzed by experts to check the performance of the AI model. There are different techniques used in artificial intelligence. Here, I listed in this slide just a few techniques, such as, for example, genetic programming, artificial neural networks, recurrent neural networks. There are many other techniques used in artificial intelligence. I will talk briefly or describe briefly one of these techniques, which is artificial neural networks. In fact, artificial neural networks, they are inspired from how a brain functions, a human brain functions. So let's see how a brain works. If we put the brain under a microscope, we will see that's made up of billions of neurons that are interconnected to each other. So these neurons, in fact, if you take one neuron, we will notice that it consists of different parts. It consists of dendrites, of a cell body, axon, and of synapses. So the dendrites, in fact, they are tree-like branches that receive information, and then they send this information to the cell body. Then the cell body is responsible of processing this information and sending a signal. This signal is then transferred by the axon, and the axon is then split into different branches, and each branch is connected to other dendrites of other neurons to transfer the signal through synapses. So inspired by this biological neuron, we can imagine an artificial neuron, which we will call perceptron, or sometimes we call it node or processing element. So the perceptron, it has similar structure to a neuron. Now neurons, they are much more complicated than that, but at least we are trying to mimic the structure of the neuron. So this perceptron consists of a cell body where the information will be processed. It consists of dendrites where the information is received from previous perceptrons. And it consists also of an output or maybe several outputs. Usually, or in a typical artificial neural networks, we'll have a series of perceptrons or processing elements as shown here. And usually these processing elements, they are arranged in layers. So you'll have usually in an ANN network, you will have an input layer, an output layer, and in between you will have one or more hidden layers. Now, a processing element, in fact, it will receive different information or different data from previous processing elements in the previous layer. So if I take this example of this perceptron, as we see, we have different data transferred to this perceptron from previous layers. We have X1 till Xn. Now, what happens in the processing phase is that every input, Xi, will be multiplied by an adjusted connection weight, Wi. And then this weighted input will be summed up for all the inputs, and a threshold value, which we call a bias, will be added to this sum. Then this input will be passed through a function, which we call in artificial intelligence an activation function. And usually it is a nonlinear transfer function. There are different types like tangent, parabolic, sigmoid functions. And this function is responsible of giving the output from this perceptron. It can be one output or two outputs. The outputs are then transferred to the other perceptrons in the next layer. So the problem, in fact, in artificial neural networks is how to choose the weights and biases. So in order to choose these parameters, there is a calibration process, or what we call training phase or learning phase in artificial neural networks. So usually we give the artificial neural network a training data set, which consists of inputs and outputs. So the network already has all the answers to given inputs. So what happens is that first we initialize the value of the weights and the biases, and the artificial neural network will process all the information following this method, and it will give an output or a result. This predicted output will then be compared to the real output, and an error will be calculated. We'll calculate the error between the predicted value from this artificial neural network and the real value from the training data set. Now, the objective is to minimize this error. There are different mathematical procedures that can be followed in order to minimize the error that I won't talk about in this presentation, as it is beyond the scope of this presentation. But there's a whole mathematical process behind to minimize the error. And following this minimizing step, we will adjust the weights and the biases in order to approach the real value of the output. So different iterations are done in order to minimize the error and to reach the best performance of the artificial neural network. Now, once this step of training or learning phase is done, and we are satisfied by the performance of the neural network during the training phase, then we move to another phase, which we call the validation phase. In this phase, we give the model another data set, which we call validation data set. And so the model will have all the inputs, new inputs that haven't been seen before, and it will predict an output. And then the output will be compared again to the new outputs in the validation data set. And then we'll calculate again the error and check the performance of this artificial neural network to see if it is giving close predictions to reality or not. So this is briefly the architecture of artificial neural networks. Now, to sum up, the development of ANN models, it consists of three main steps. So first, preparing the required data for training the network, then evaluating neural networks with different structures and choosing the optimal one. Because as I mentioned previously, there are different hidden layers, and in each hidden layer, we have different hidden nodes. So how can we choose the number of hidden layers or the number of hidden nodes? Usually this is done by trying different architectures, and then we choose the architecture that gives the optimal result. And finally, we have the phase which consists of the validation phase, where we test the neural network's performance using data which have not been seen previously for training the network. So now, what about AI in geotechnical engineering? I have presented some of the techniques used in general in artificial intelligence, and I described ANNs, but how about the applications of AI in geotechnical engineering? In fact, nowadays and recently, we are noticing that there are many studies done using artificial intelligence in general. So there are different areas where artificial intelligence is being applied. For example, deep and shallow foundations, soil stability analysis, dams, maintenance, tunnels, pavements, soil liquefaction, many applications. And a recent study has shown that there are many studies done using AI in different areas of geotechnical engineering. And it's interesting to see that most of these studies, they use ANN, artificial neural network technique, in order to develop the artificial intelligence models. So AI is being used because it has lots of benefits, especially compared with other traditional methods. So some of the benefits of AI include the following. In fact, AI models, they can solve highly nonlinear complex engineering problems that sometimes traditional methods might fail to solve. In fact, as I mentioned previously, AI, it is a data-driven model. So it relies only on the data in order to determine the structure of a phenomenon without any assumptions about the physical behavior of that phenomenon. And this is in contrast with other physically based methods that usually they rely on physical laws in order to determine the underlying relationship of the different elements in a system. And usually they are done by lots of assumptions and simplifications of the physical problem, and even they require prior knowledge of the relationship between the different parameters. So this point is considered as an advantage for AI in comparison with traditional methods. Now, another benefit is about the fact that AI deals with multidimensional problems with any number of inputs and outputs, and it can be optimized to the most significant inputs. So for example, deciding the number of parameters to choose as inputs to the model, can be done by first the expert who is developing the AI model, and also in an artificial intelligence model, we can study the importance of each input parameter. And based on that study, we can decide if an input is really participating in creating the output or not. And also AI can be updated to obtain better results once more data are available. So whenever we have more data, we can improve the artificial intelligence model. And AI models, they deal also with noisy or missing or uncertain data, which is relevant to solve geotechnical engineering problems, as we suffer from these problems in geotechnical engineering. So these are some of the benefits of AI. Now, despite all these advantages, AI models, they also have some limitations and challenges. For example, the governing parameters in an AI model, they must be decided in advance using trial and error approaches. As I mentioned previously, to decide the architecture of an AI model, usually we have to try different scenarios, like for example, one hidden layer with one hidden node, or two hidden nodes, or two hidden layers. You have to try different scenarios, and even the activation function can try several activation functions. And then choosing the architecture, the AI architecture that gives the best or the optimal results. Another limitation is the extrapolation beyond the range of data used for model training, which is questionable. In fact, when we train the model, usually we give input data points which correspond to a given range of values. So the model is trained in this range of values. Now, if I ask this model to predict given behavior by giving this model input parameters outside this range, then we're asking the model to extrapolate, and this might not lead to correct predictions. Another limitation is that AI models, they are usually criticized of being black boxes. This means that there is a lack of transparency in AI models, or where the physical meaning of the relation between inputs and outputs, it's not always clear. But usually, in fact, what's done now is that AI researchers, they address this issue, and they're trying to develop, by the end of the AI model, an equation or a relation between the inputs and the outputs. and then they perform sensitivity analysis, and therefore giving more a physical meaning of this relationship between inputs and outputs. And we will see that in one of the applications later on. Now, another challenge of using AI in geotechnical engineering is the reliability of data. In fact, when we need to build or to develop an artificial intelligence model, we need to use the right data set and to have a trusted source of data that are clean, accessible, and secured. So usually, in fact, it's not always possible to access data. Sometimes if we ask an owner of a geotechnical structure to give us the data, he or she might not accept. And sometimes the data is secured that we can't reach. So these are some of the challenges that we face when we try to develop AI models. Now, how about the applications in geotechnical engineering? Now I'm going to give some examples of applications, and these examples, they are from literature review. So I'm not the researcher who worked on these applications. There are other researchers who worked on them. I'll just present how they developed the artificial intelligence models and the performance of the models they developed. So starting with the first application, it is about the prediction of the settlement of shallow foundations. So in fact, in this study, they used a database which consists of a total of 189 individual cases of field measurements of settlement of shallow foundations. And the data covers a wide range of variation in footing dimensions and cohesional soil types and properties. And using this data set, they developed an artificial intelligence model based on artificial neural network technique. And in fact, developing, as I mentioned previously, to develop an AI model, this is an important and also a difficult step, as it requires knowing the number of hidden layers, number of nodes, what inputs to include in the model. So in this study, they found that after several tries and errors, they found that one hidden layer gave a good performance in the training of the model, and with two hidden nodes. And for the output layer, they used only one node, which is the measure of the settlement. And as input parameters, they used the footing width, the footing net applied pressure, SPT block count, and footing length and footing embedment. So using this AI model architecture, they were able to get the predicted value of settlement and to compare it with the measured ones. And also they compared the performance of the AI model with other traditional methods such as Mayrov, Schultz and Sheriff, and Schmertman. And in this table here, I show the performance of ANN compared with the other traditional methods in terms of coefficient of determination, root mean square error, and mean average error. So as can be noticed that the artificial neural network, it has a higher coefficient of determination. It's more accurate than the other methods, and it has smaller errors than the other methods. And as can be seen from these figures, the ANN model was able to predict quite correctly all the measured settlements. However, the traditional methods, they predicted correctly small values of settlements in the range of 10, 20 millimeters. However, for higher values of settlements, they either underestimate or overestimate the settlement value. So this is one application showing how powerful an ANN method can be compared to other methods. Now, another application is about the of load settlement curve of driven pies. So in this study, the researchers were interested in predicting the full load settlement curve, not only the bearing capacity or only the settlement. Because in fact, usually the design of the pies, usually in traditional methods, it relies on bearing capacity alone or settlement alone. So the prediction of the load and the settlement is done separately. However, based on filling years, it is shown that the bearing capacity or the soil resistance and the settlement, there are two parameters that are influenced by each other. And so it is important for the prediction of PI's load settlement curve. It's important, in fact, to predict the full load settlement curve. So in this study, researchers, they got a database from the literature, and the database consisted of PI load tests and CPT tests, compenetration tests. And these tests were done on sites with different soil properties and geotechnical conditions, ranging from cohesive clays to cohesionless sands, and also with layered soils. So to develop the AI model, in this study, they used a recurrent neural network. It's somehow similar to ANN, and we will see later on the architecture. But in this method, in fact, what's interesting, because we need to predict the full curve, and predicting the full curve means that the current state of load and settlement will govern the next state of load and settlement. So to predict, for example, the load at the state I+1, this will depend on the load, on the value of the load at state I, and so on. At Qi+2 would depend on Qi+1. So the architecture of a recurrent neural network is as follows. So we see that the prediction of the load at the next loading state would depend on the pi load at the previous loading state. So to decide the architecture, again, several trial and errors were done in order to predict the optimal architecture. And in this study, one hidden layer was used with 10 hidden nodes, and the output was only one value, which is the pile load. And the inputs consisted of the pile geometry defined by the diameter of the pile and the pile embedment length. And for the soil properties, because we have a layered soil, in order to take this into consideration, in this study, they used averaged values. So they used the weighted average comb point resistance over the pile tip failure zone, and the weighted average friction over the pile tip friction zone, and the weighted average comb point resistance over the pile embedment length, and the weighted average friction ratio over the pile embedment length. Other parameters in the input consisted of these three current states, which correspond to the normalized axial settlement, the increment in the axial settlement, and as I mentioned previously, the pile load at the current state. In this study, they used for training the model, a training data set, which consists of 20 pile load tests. And for the model validation, they used 3 tests. And the results, and here are the results for the training data set and on the validation data set. As can be seen, the model was able to capture correctly the experimental results. So we can see that the model points where they fit perfectly, quite perfectly, the experimental data. And also we can see that the AI model succeeded in simulating the nonlinear behavior of the similarity to the experimental results. And concerning the performance of the models through the coefficient of correlation and the calculation of the coefficient of determination, we can see that the performance of the model in training and in validation is quite well. Now, in order to generalize the predictive ability of the model, and in order to test the robustness of this model, a sensitivity analysis was done. So in the sensitivity analysis, what's done is that we try to fix all input parameters and only change one of the parameters, and try to see if the model will be able to capture the illogical behavior based on our geotechnical knowledge. So for example, In this study, they tested the effect of pile diameter, pile length, comb point resistance at pile tip and at pile length. And they noticed that the model captured the relationship between the different parameters and the logical geotechnical behavior. So we can see that the bearing capacity increases with pile diameter, increases with the pile length, with the comb point resistance at pile tip and along pile length. So this gives more confidence in using this AI model. So how can engineers use this AI model? In order to facilitate the usage of this model, we're able to develop an executable program that can be used by any researcher or engineer, any interested researcher or engineer upon request. So whoever wants to use this simple application can just ask us and we can give them this application. In fact, an AI model will then help us to establish an equation or a relationship between inputs and outputs. So we can use this relationship and implement it in a simple user-friendly application as we did here. So what we can do then is just provide this application by the input parameters and we'll get the predicted load settlement curve. Similarly to this study, another study is still ongoing. The objective of this study is to predict the load settlement curve also of pile foundations on Dubai sedimentary rock. We are mainly interested in the business bay or Dubai, the downtown of Dubai areas. And in this area, in fact, we already have a good data set, which consists of 116 static load tests collected from more than 45 towers in the business bay and downtown Dubai areas. So why we are interested in this study, and also we have lots of geotechnical and geological data. So we're interested in this study because based on previous researches, it was found that conventional methods used to design pile foundations might lead to additional over-design of the pile dimensions. And this can result in additional material and labor and therefore increased costs. So in this project, we will develop an artificial intelligence model in order to predict the load settlement curve of piles and compare them with other conventional methods. Our objective would be to help engineers optimize the design and the analysis of the piles in Dubai sedimentary rock and therefore participate in green construction. Now, this model will not only be used for Dubai sedimentary rock, but it can also be used for other areas with similar geological and geotechnical conditions. The project is still ongoing, so I won't be able to share with you any results, maybe or hopefully in future presentations. Now, another application, it's related to the prediction of the mechanical behavior of railway ballast. In fact, ballast are among the most used materials in railway tracks. And we already know that ballast, they are subjected to high levels of stresses due to the heavy loads of trains. And so it is important to study the mechanical behavior or to be able to predict accurately the mechanical behavior of the ballast once subjected to static and dynamic loadings. So in this study, an artificial intelligence model was developed, and it is based on a database consisted of 29 large-scale triaxial isotropically consolidated drain compression tests that were conducted on 3 of the most commonly used types of railway ballast. And in this study also, they did finite element modeling using Plaxis, using one of the hardening models. So these results are used for comparison later on with the predictive ability of the AI model. So for the AI model, they also used recurrent neural networks. So this is the general architecture of the AI model used. They used one hidden layer with 10 hidden inputs. And in this AI model, two outputs were predicted: the deviator stress and the volumetric strain, because they needed to predict two figures or two curves: the deviator stress versus the axis strain and the volumetric strain versus the axis strain. And the input parameters consisted of different parameters, some parameters that correspond to the grain characteristic or the characteristic, such as the D50, the diameter at which 50% of the specimens pass through the sieve, CU, which is the coefficient of uniformity, coefficient of curvature, CC, and also other physical parameters as void ratio, bulk unit weight, and stress state parameters such as the confining pressure. And the current state parameters also they use the. So using this AI model, they were able to predict the deviator stress curve versus axis strain and the volumetric strain versus the axis. As can be seen in these figures, the AI model succeeded to predict the experimental data, and compared with the FEM results, you can see that even the AI model gives better results, especially that in the FEM model, it was a hardening constitutive model. So the post-peak softening, it wasn't very well or perfectly captured. In the AI model, we can see that the hardening and the post-peak softening was well captured. And even the contractancy and the dilatancy was well simulated. And also the effect of the confining pressure was also well captured by the AI model. Now, what about the future of AI in geotechnical engineering? In fact, with the concept of artificial intelligence and putting data into action, nowadays there is noticeable efforts in order to investigate the digital transformation of geotechnical engineering field. So the future of AI, I can say it's all about the digital time. And according to one of the presentations given by Professor Mark Gilorami, the next phase of AI revolution would be through digital twins. So let's explain let's define what are digital twins. A digital twin, it is a replica or a virtual replica of a real geotechnical structure or real structure, any structure. And it serves as a digital counterpart for purposes such as testing, live monitoring, maintenance, and others. And so a digital twin can be used in real time, and it can be synchronized with corresponding physical systems. Let's see some examples about the applications of digital twins. One of the applications is the Diablo Dam. In fact, the Diablo Dam, it was built in 1936 in northwestern Washington. And the objective of creating the digital twin was to ensure the safety of the dam. So a virtual replica of the dam was created, and it allows, it was also connected with sensors, with on-site sensors, in order to allow real or live monitoring of the dam. And through machine learning and artificial intelligence, it is always possible to predict or determine how the geotechnical structure could behave or change with time, such as, for example, we can predict or we can even monitor erosion of the surrounding soil or automatically identify cracks. and other changes in the dam. And this can allow operators to take corrective measures and therefore immediately improve the maintenance of the structure. Another example of digital twins in geotechnical engineering is in the field of slope stability and safety on construction sites. For example, a digital twin can give us alerts about any movements that can be detected of a slope, any movements of a slope that can be detected on site. So this can even help us to do real-time monitoring of the site and even maybe plan ahead for optimum slopes. Another important application of digital twin is in the field of safety on construction sites. For example, digital twins in parallel with artificial intelligence, it can help us identify any misuse of personal protective equipment, such as safety helmets or vests, and so that we can immediately interfere to protect workers on site. So there are lots of benefits of digital twins in geotechnical engineering. Among these benefits is the real-time monitoring of the geotechnical structure. For example, and other benefits can be allowing efficient consumption of resources, allowing testing what-if scenarios, including, for example, the impact of design changes or any events that can occur. And also, digital twins can allow for efficient management and to improve productivity and safety. Now, again, besides all these benefits or advantages, there are also some challenges that we might face in digital twins projects. For example, it is essential to remain aware of the quality of the data. In fact, a model is only good as the data that created it. So it's very important to have good quality data, to have a model that can be really useful for us, for the geotechnical engineers. And the twin model is only useful as long as it remains updated by integrating new data as conditions change. If new real-world information isn't fed back into the digital twin, it might become misleading. And so finally, I'd say in today's world, which is a rapidly changing world, it's time for geologists, for engineers, for structural designers to get to know digital twins. For it offers many exciting and new possibilities for safer and even more efficient design and better understanding of risks and uncertainties. In other words, it brings words of information together. So I'll conclude by some acknowledgements. I'd love to acknowledge Professor Mohammed Shaheen and Dr. Marwan Al-Zailai for they shared some of the material that I presented in this presentation. So thank you. Thank you for listening. And if you have any questions, feel free to ask.
Thank you, Dr. Rodaina. It was really very attractive and very challenging on the topic and presentation. And I think there is a long way for us to go in order to catch up with the applications of AI in geotechnical engineering. Before we go to questions and answers, I have just a small note to mention about our webinar program. Next month on December, there will not be a webinar on the TTalk program because there will be a geotechnical summit arranged by DFI Middle East in the Big Five event on the 5th of December. It will be in the Dubai World Trade Center. You can check the website for more information, and we hope to see you there. We will try to resume on January and after that, and the announcements will be made by them. Thank you again, Dr. Rodaina. I think we have one question is now there, but I hope that others can just cast their questions in the chat box or on the question and answer. On the chat box, I can see one question. Can the technology predict the settlement induced by thermal cycles loads? This is
Yes, yes. In fact,
engineering.
whenever you have data related to a given problem, then you can use the data to transform it into an artificial intelligence model to predict the settlements. But you should have clear data. You should have, for example, enough enough results about the settlements related to thermal cycle loads. So if you have enough data, then you can develop an AI model.
Thank you. Maybe I have one question about how a company can be oriented now towards artificial intelligence applications. Actually, we have been working in geotechnical engineering in the Middle East for many years. And we have a lot of data. We run laboratory as well. We know the geology very well. We have lots of information on ground conditions, material properties, pilot tests, foundation performance, building performance as well. But what is the advice that you tell us how to be oriented, towards, arranging ourselves and putting our mindset towards the use of artificial intelligence?
Yeah, in fact, to tell you, there are many companies that are very interested in artificial intelligence nowadays. And we are even contacted by many companies to work with them on developing artificial intelligence models. So they already have this mindset now about the importance of using artificial intelligence in geotechnical engineering. Sometimes, in fact, companies, they are using this method as a complementary method with other conventional methods. Like they don't want, and they can't get rid of conventional methods, but they need another complementary method based on artificial intelligence to help them predict maybe more rapidly the behavior of the soil. This can avoid, in order, for example, to avoid doing on-site tests, field tests, they gain time, they gain money, and they just use artificial intelligence. So the companies, they are already very interested by AI and by digital twins as well.
Okay, there's one interesting question also. For someone who does not have experience in AI, where and how to start the basics, especially for geotechnical engineering?
Well, well, there are different ways. If that person needs to learn AI, then the first step is at least to understand the concepts of AI, how an AI model works, how it functions, how to build an AI model. But if the person doesn't want to study AI and just use the AI as a tool, this is what I showed in one of the applications where we developed an application or a mini program for engineers that can be used immediately without any knowledge about the artificial intelligence architecture. So either you learn the method yourself and you build your own artificial intelligence model, or if you're just a user, you want to be a user of the model, then use another program developed by artificial intelligence engineers or researchers.
Thank you. One long question. A large obstacle, I would imagine, is obtaining large, reliable data sets for the various locations across the world. Is this a big obstacle? How would you propose to overcome the potential hesitancy of stakeholders, owners, geotechnical engineers, etc., to realize their data, to release their data for use in consulting better, more reliable models when it conflicts with their business interests? It's a very, very interesting one.
Yeah, it's a very important question because, as I mentioned, it's one of the challenges to access data or to ask stakeholders to share with us their data. Unless they are convinced, they won't share. So we try as much as possible to convince them to share their data, to convince them by the benefits of building or developing artificial intelligence models. Sometimes we succeed, other times we don't. And concerning the other part of the question about the obtaining large data sets for various locations across the world. In fact, what's interesting in AI model, even if I don't have a very large data set, I can still start by developing this model using the data set that I have. It should at least be enough to build an artificial intelligence model. But then this model can always be improved if I get a new data set. So whenever I'm able to get a new data set, I can integrate it into the model and improve the prediction of the model. Well, to have data sets from all around the world, it would be an obstacle. It would take time and it would need the collaboration or the cooperation of different maybe companies, researchers, engineers to work together to be able to develop such a general AI model that can work for any place around the world.
What's the best format you think to have the data stored with? You know, there are programs or there are data formats or recommended method for storing the data, because most of the data we have, mainly you can find it on Excel, you can find it on PDF, you can find it on AGS. Is there any preferred method to store the data?
There's no preferred method. It depends on the one who is developing the model, which method suits him or her better. For example, some prefer Excel sheets and then to use the Excel sheets as input files for the model. Others might prefer text files. So it depends on the programmer or the model.
Thank you very much. I think there are no more questions. Anyway, anybody who has any further questions, they can, of course, communicate with DFI Middle East. They can also check the website. The recording will be also given on the website for DFI members. So if you are not a DFI members, you are highly encouraged to get your membership to enjoy the many benefits from the membership of DFI. Thank you very much again for attending, and thanks to Dr. Rodaina. And I'm sure that this was a very beneficial session for all of us. Thank you, Dr. Rodaina.